Well, today I will talk about a new topic, that is scattering cross section. As I told earlier in the earlier playlist of this elastic and inelastic collision, that is started with the 4.1 and the 4.2 and so on. I talked about all these lectures, and after that there is another very important article is remaining with us, that is the scattering cross section. It's a very important uh, problem with us. So first of all, let me talk about that. What is scattering? So scattering is the phenomena where a particle or the wave is deflected from its original path due to interaction with another particles or an inhomogeneity in the medium it is traveling through. So this deviation can be manifested in various ways. Sometimes the direction will also change, or sometimes the energy will change, and sometimes there is a change in polarization, and so many other things. For example, say this is a particular center, and say flux of particle is coming in this direction, and they are changing their directions and changing their velocities, so that this process is known as means after colliding this scattering center, some particles may go like this, some particles will go like this, and some particle will go like this. So this process is known as a scattering process. So let me show you one animation of this. Basically there is a small Python script with us. Yeah, this is a Python script which I am using here, and I put it on my web page also. It's a small Python code, and say if I want to show you, then it will work very beautifully. Let me show you the see how the particles moving when they are bombarded on some target. See, so that's what is happening. Particle will move in the different directions. So you can use this animation also for this to visualize it. Now next is how to mathematically work on it. So first of all, to work on mathematically, we have to understand the meaning of the scattering cross section, that what is scattering cross section. So suppose there is a dartboard with me. Just a minute. Yeah, let me change this. Let me put it somewhere here. And yeah, so now suppose there is a dartboard with me. This is one dartboard, there is another dartboard, and I am hitting something on it. Say it is a dartboard and I am hitting something. So that means it is a scattering cross section. But if we are having a bigger dartboard and we are having a smaller dartboard, then it's very easy to hit on the bigger dart one. There's more probability that we can hit it, but sometimes we are not able to hit it. And but for the smaller dartboard, it becomes very difficult to hit with a dart, right? So scattering cross section is also like that. It is also in that way. The scattering cross section is like the size of that dartboard. So in physics, we measure how likely a particle or like a dart is to hit the target. That is dartboard. Means if bigger cross section is there, then the higher is the chance of hitting, and if a smaller cross section is there, then the lower chance of hitting. Say if I am hitting this dartboard, say this is a one dartboard and this is another dartboard. So if I am hitting and throwing something towards this, say I'm throwing a dart in this direction, few darts may hit and few may go outside. Sometimes it may also happen. So scattering cross section is like that. It is related to the area of the target, right? In a very simple sense, if I try to look at that. Then let me talk about that, what is scattering cross section and what is the probability scattering. So what will happen when we send some particles, or the flux of particles is coming then and made to incident over the target, then what will happen? Few particles are scattered elastically, so it is elastically, sorry, and few remains unscattered, means few particles will go like this, and other particles will scatter inelastically. So what is the probability of scattering? Probability of scattering is number of particles scattered elastically to the total number of particles incident over the target. Right? This is a one way to look at the probability of scattering. So suppose A is the area. Suppose there is a area A, target area is A, means say it is a target area, and say its area will be A, and it consists of n number of particles, say like this, n number of particles are there inside it, and say I is the incident flux density. Incident flux density means the particles incident per unit area over this, say it is a unit area per unit time. See how many particles are made to incident over this area per unit time, and then the total number of incident particles per unit time is also represented by intensity into A, because the large number of particles are coming. So I into A gives us the total number of incident particles, a flux of particles which is coming and made to incident over the target. Now NS is what? It is the number of particles scattered per scatterer per unit time. Means how many particles are scattered elastically. Means there are so many scatterers. Say once this is, suppose I am considering this scatterer, and say how many particles it is scattering per unit time, then that is represented by NSC. So therefore number of particles scattered per unit time is represented by N into NSC. So therefore probability of scattering is defined as the N NSC divided by this one IA. So this is the probability of scattering. This is the ratio of these two quantities, right? This is the probability of scattering. Now let us try to look at all these things mathematically, because mathematics formulation is needed to look at this very beautiful concept, because the beautiful example of this scattering process is the Rutherford scattering, and that help us to look at the size of the nucleus. So before talking about the Rutherford scattering, I want to discuss with you this basic definitions which are needed in later on. So this is the one thing which I have defined, that this what we call this is scattering in the earlier slide what I have shown you. Probability of scattering. I talked about the probability of scattering, and the probability of scattering is basically NSC over IA. Now but say this is my target element, these are the, say this is my target, and say its area is A, but its effective area of each scatterer is, say, sigma SC. It is the effective area, and this is the effective area. Let me define in terms of this. So therefore total effective area will become, because if this scatterer contains n number of atoms, then the total effective area with n target particles is given by n sigma SC. Then what is probability of scattering? This is the earlier definition which I talked about. Now the probability of scattering is what? This is the total effective area divided by total area. Earlier I defined in terms of the incoming flux density. Now I am talking in terms of what? I am talking in terms of area. So total effective area is what? Total effective area and sigma SC, and total area is A. So these both the things are defining the one and the same quantity. It means both are talking about the probability of scattering, and that means both can be equated mathematically. So if I equate these two quantities, then what will happen? NNSC divided by IA is equal to N sigma SC divided by A. This will cancel out with it. So I can write down it as sigma SC is equal to NSC over I. So this is the scattering cross section. So therefore I can write down it says the scattering cross section is equal to cross section, or sometimes it is known as geometric cross section. It is equal to this, it is N over NSC over I, or we can say that, in other words, I can write down it as it is the ratio of basically number of particles scattered per scatterer. It's a very important thing. This is per scatterer, the way in which we have defined it in this way: per scatterer per unit time divided by number of particles incident per unit area per unit time, or we can also call this denominator as a flux density incident so this is a way that how the scattering cross section can be defined. This is the scattering cross section. Now let us try to look at it in a different way. There is another way to look at this thing. So suppose, let's say this is a target and the particles are coming in this way. When it comes in this way, it will go in this direction. So it is, say it is scattered through an angle theta. If it is scattered through an angle theta, then how it can be defined? And after, say another particle is coming, it will go like this. So then say its angle will be, said that's a theta plus d theta. Its angle will be theta plus d theta. Then suppose n number of particles, those are scattered through an angle theta. N number of particles which are scattered through an angle theta, when they come closer to this scattering center, this is known as a scattering center. Then how we can define? We can define scattering cross section or the differential cross section, because I am talking about a very small angle. It's a particular small angle. So that means I can define scattering cross section is like this. It's like a differential cross section. So particles are coming with the intensity I, and the number of particles which are mazed to incident over or which are scattered through an angle theta. Now that means I am defining scattering cross section in terms of angle. So say it is n theta is this one. So this is known as the scattering differential cross section. This differential cross section, means for a particular angle, say it will go like this. Now suppose few particles, they are scattered through angle theta plus d theta, then it will make a type of annular ring here, and this is a small region which is making an angle d omega here, and this is known as the solid angle. So therefore scattering cross section sigma theta with d omega, it can be written as n theta over I into d omega. It can be written like this. So what is it? What this quantity is representing? This is basically number of particles scattered per second into solid angle d omega, or annular ring between phi and sorry, not phi but the theta and d theta, theta and d theta. So what does it mean? Therefore I can write down it as a, from here if I do little algebra, so from here I can write down sorry, this is not this, but yeah, which implies from here I can write down it as n theta d omega is equal to I sigma theta into d omega, and this is basically number of particles, right? This is not right. So let me put it from here. Just yeah. So this is it basically, yeah, and this is not needed. Yeah, so that means this is the number of particles. This quantity is basically represents this value, right? So now I want to find out the total cross section, and say this is it. Yeah, and theta d omega is equal to I sigma theta, and it is sine theta d theta and d phi. Right, this is the value of this solid angle, and it is a sine theta d theta and the d phi. As for annular ring, that phi varies from 0 to 2 pi. So therefore I can simply integral of d phi for the one annular ring. I can write down it like this, and it is equal to 2 pi. So I simply put it 2 pi here. So therefore this is equal to 2 pi I sigma theta, and it is sine of theta d theta. That's what I'm getting here. So therefore I can derive the total cross section from here also. So total cross section I can write down it as like this. So therefore total cross section sigma theta d omega, if I take its integral, then it can be done like this. So it is basically because I am interested to find out this quantity total cross section. So this is it basically, sigma theta 2 pi sine theta and the d theta, and here only one quantity is changing, so that's why I can write down it as a this one sigma theta, and it is a sine theta d theta, and simple replace this triple integral into a simple integral. So this is the total cross section. So this is defined as the total cross section, right? So this is a way that how we can look at the differential cross section, total cross section, and we define the probability of scattering. And also very important thing, that is the unit or the dimensions. So as we know that this sigma is basically, it is n theta over I, and I, this n theta is the number of particles per unit time. So per unit time is sitting here, its dimension will be t minus 1, and here intensity is the number of particles per unit area and the per unit time, so it is t inverse then the L inverse square. So these are its dimensions. This will cancel out and it will become L square. So that means it has the dimensions of the area, basically scattering cross section. And when we talk about the nuclear cross sections, means when we talk about the nuclear physics or the Rutherford scattering, that means the nucleus is a very small, and in that case we will use its unit as a barn, and barn is basically 10 raised to 28 meters square. That's what we know that, right? So I think that's all for this lecture, and it's a brief idea of say it's a scattering and the scattering cross section. And in the next lecture I will talk about Rutherford scattering, and I have also shared with you some other examples, so you should also go through all those also. And that's also the common lectures which I given in the advanced quantum mechanics. They may also help you out. And there is another very important, I have forgotten that there is a basically a impact parameter which we want to show you. Impact parameter also a very important thing. Let me talk about impact parameter. What is impact parameter? So say there is a one ball and there is another ball, and say it is approaching this one, so it will hit it here. But if it is coming this way, I am just talking about the classically, then it will not touch it, it will go as it is. But here it will hit it here and it will go this way. So that means the closest perpendicular distance between, say it is the its axis, and say the perpendicular distance between these two of the closest approach of these two, this is known as the impact parameter. So here the say in this case the impact, it is the radius of this, say it is, if it is a spherical scattering center, and it is the radius of this is this one, and say there is another ball which is coming here, or I can say that is a classical particle, if it is approaching it here, and if this perpendicular distance between these two, it's b is less than r, then it will hit it, and if b is greater than r, or it is equal to r, it will not hit it. So here the b becomes a very important parameter. So impact parameter, we call it as a impact parameter. So this will also help us in the various, so this is a very important definition. So I think that's all for this today's lecture.